Quantum mechanics, a branch of physics that emerged in the early 20th century, has undoubtedly shaped modern science in profound ways. The theory revolutionized our understanding of the microscopic world, challenging classical notions of physics and paving the way for technological advancements that have transformed various fields of study. Here, we will explore some key aspects of the quantum revolution and its impact on modern science. Wave-particle duality. One of the central concepts in quantum mechanics is wave-particle duality. Classical physics described particles as discrete entities with well-defined positions and velocities. However, quantum mechanics introduced the idea that particles, such as electrons and photons, exhibit both particle-like and wave-like properties. This concept was established through experiments like the double-slit experiment, which demonstrated the interference patterns produced by particles behaving as waves. Wave-particle duality challenged the Newtonian worldview and led to a new understanding of the fundamental nature of matter and energy. Uncertainty principle. Another fundamental principle in quantum mechanics is the Heisenberg uncertainty principle, proposed by Werner Heisenberg in 1927. It states that there are inherent limits to the precision with which certain pairs of physical properties, such as position and momentum, can be known simultaneously. This principle shattered the deterministic worldview of classical physics, highlighting the inherent probabilistic nature of quantum systems. The uncertainty principle not only has profound philosophical implications but also forms the basis for various technological applications, such as in quantum cryptography and quantum computing. Quantum superposition and entanglement. Quantum mechanics introduced the concept of superposition, which states that quantum particles can exist in multiple states simultaneously. This means that until a measurement is made, particles can exist in a state of being both here and there, or in a combination of different energy levels. Additionally, quantum entanglement refers to a phenomenon where two or more particles become linked in such a way that their states are correlated, regardless of the distance between them. These concepts have sparked significant interest and research in the fields of quantum information and quantum computing, offering potential for unprecedented computational power and secure communication. Quantum mechanics and technology. Quantum mechanics has had a profound impact on technology. One notable example is the development of the transistor, which is the fundamental building block of modern electronics. Transistors exploit quantum mechanical effects to control the flow of electrons, enabling the miniaturization and increased performance of electronic devices. Quantum mechanics has also paved the way for other technologies, such as lasers, magnetic resonance imaging, MRI, and atomic clocks, all of which rely on the understanding and manipulation of quantum phenomena. Quantum field theory and fundamental interactions. Quantum mechanics provided the foundation for quantum field theory, which describes the behavior of particles and forces at a fundamental level. Quantum field theory unifies quantum mechanics with special relativity, allowing physicists to study the interactions of particles through the exchange of virtual particles. This framework led to the development of the Standard Model of particle physics, which describes the electromagnetic, weak, and strong nuclear forces. The successful predictions of the Standard Model and the recent discovery of the Higgs boson at the Large Hadron Collider highlight the power of quantum field theory in understanding the fundamental building blocks of the universe. In summary, the quantum revolution, driven by the principles and concepts of quantum mechanics, has fundamentally shaped modern science. It has challenged classical physics, provided new perspectives on the nature of matter and energy, and enabled the development of technologies that have transformed various fields. Quantum mechanics continues to be a vibrant area of research, promising further breakthroughs and applications in the future.